Okay, so today we are going to talk about a relativistic theory for gravity. So what is the starting point? The starting point is that we decided that the symmetries of our theories that describe nature should be Lorentz symmetry or Poincare symmetry. And now we want to construct a theory of gravity that respects this symmetry. And of course, we also want to construct a theory that agrees with whatever we knew before, reproduces the answers that we get from reproduces the successes of the Newtonian gravity. So the starting point is to see how we can write a relativistic version for the Newton's equation, Newton's law of gravity. Well, this is the starting point, but the way I started is not the conventional way to start discussing GR. But now that we have learned about the quantum field theory or a combination of quantum mechanics and special relativity, now we know that we have particles. So if you have interactions between different degrees of freedom, those interactions are mediated by the exchange of various particles, as for instance you are going to see in the exercise. And so one of those interactions is the gravitational interaction, and we expect the same thing. There has to be a degree of freedom, some particle that mediates this gravitational force. And then the question would be, what should we choose? What kind of particle would do the job? And of course, the easiest candidate to consider is to consider a scalar particle, a spin zero particle. So we want to try to see if we can find some relativistic description using a scalar particle that reduces to this Newton's equation in the non-relativistic limit. Right, so the task is kind of very well defined. Of course, the easiest thing that I can do here is that this equation is of course non-relativistic. It doesn't make any sense in relativity because I have Laplacian here. And it describes some instantaneous interaction. The version that would make sense in special relativity, one possibility would be to just replace this Laplacian by a D'Alembertian, dt squared plus Laplacian, keep this phi gravitational potential, but now promote it to a scalar field. And then the object that I'm putting on the right hand side of this equation is minus the candidate that we have. So what is this rho? Let's discuss the candidate for the right hand side. So what is this rho? This rho is the density of masses, right? So we want to put an object which is, and this equation, so this is the left hand side is the Klein-Gordon equation for massless field. The left-hand side is just a scalar. So what appears on the right-hand side should also be a Lorentz scalar. So we want to find a Lorentz scalar that resembles rho or reduces to rho, the mass density, if we go to the non-relativistic limit. My claim is that, and we are going to check this, that candidate is the trace of the stress energy tensor. This is the most natural object that exists in the relativistic theory. The stress energy tensor is something that knows about the energy and the momentum. And then energy, we know that in the non-relativistic limit reduces to mass. So there is a hope that this quantity reduces to rho. In fact, this sign is chosen such that it does. And it is a scalar because I am tracing summing over the repeated index. Okay, so now, of course, when I consider the spin zero particle, maybe that was even an earlier consideration. Even before talking about what should be the spin of this degree of freedom, you can answer the question what would be the mass of this intermediate particle. And the mass has to be zero. So if we want to, what are we doing? We want to go to a relativistic theory. And the question is, for instance, what is m phi, or m of, let's call that degree of freedom the graviton. So what is m of graviton? And what is s, the spin of graviton? We should answer, first of all, we should answer these two questions. Since we learned that the representations of Poincaré are this characterized by whether we are mass, what is characterized by mass and by spin or helicity, if we are talking about massless one. So the answer to the first question is that m has to be zero, because if we consider massive particles, then they introduce a short-range force. While gravity, we know that it's a long-range force. It's not. It's a force that goes as 1 over r squared. While if I have a non-zero mass for my force carrier, that would correspond to a force that exponentially dies at distances much larger than 1 over mass. So to be very specific, if you imagine adding a mass term to this equation, some m squared, m graviton squared times phi, and imagine you put a point source here, so there is no time dependent. You can calculate what is the potential, and therefore what is the force law that you get. And you can easily see that potential will be something that goes as e to the minus m graviton r divided by r. So at distances larger than 1 over m graviton, the potential will exponentially go to 0. And since this is not observed, at least it puts an upper bound on the mass of graviton. So we have explored gravity, checked gravity at large distances. We don't see any indication for such an exponential decay of the gravitational force. So that puts an upper bound. When we go to higher spins, then there will be even more constraints. But at least just from the range of the interaction, we know that this m graviton has to be, if not 0, has to be tiny. So we can, for the moment, just set it to 0. And then yes, then the second question is what is the spin? And now we are just exploring possibilities. And of course, the first thing to check is to consider a scalar s equals 0. Okay, so now let's justify putting minus trace of the stress energy tensor here. What is the easiest way to see? By the way, in my notes, sometimes my conventions change for the sign. Now I try to uniformize them, but it doesn't. At the end, it doesn't really matter if you recover the correct answer. So of course, one can define t in various ways. I mean, one can put a sign in front of it. Doesn't change the physics. So what the way to verify this choice is, or sorry, let's before talking about that choice. So we want to verify that in the non-relativistic limit, we go back to the Newton's equation. So let's first look at the left-hand side and see that it does go back to the Newton's equation. And the reason for that is that when we go to the non-relativistic limit, that means that we are considering small velocities, or in other words, delta x divided by delta t is much less than 1. Remember that we set the speed of light to 1. But that is equivalent to saying that time derivatives are much smaller than a gradient, a space derivative. So in the non-relativistic limit, the left-hand side does go to the origin, I guess. Meaning that the spatial gradients are much more important than time dependencies if you have a non-relativistic system. Okay, so this is for the left-hand side. Now for the right-hand side, let's look at the T mu for a point particle. So the T mu for a point particle is, let me look at the T mu with mixed components. So this is given by P mu divided by P0 times delta 3 of x minus x of t, where this big x of t is the trajectory of our point particle. So let's first see that this is the correct stress energy tensor for a point particle. So how do we verify that? We look at various components. We know that the stress energy tensor is supposed to give me the energy density and the momentum density. If I look at the component with mu set to 0. So the zeroth component, if you remember in the derivation of the nodal theorem, the upper 0 component would correspond to the density of whatever conserved charge that we have. So T0, 0 has to give me the energy density, and T0, I has to give me the momentum density. However, one thing to keep in mind is that since we are working with the mostly plus signature, then 0 with lower, so P0 with upper and P0 with lower differ with a minus sign. So there will be this minus sign to keep in mind. So if I look at the T00, that would be P0 times delta 3 of x minus x of t, which is the correct density of energy with lower indices of P0. And also if we are, or in general, maybe I'll just summarize it here. This expression is correct because it gives me the right density for the forward momentum of the particle. And then if I take the trace of that expression, again, this convention P is the trace of P mu times P mu. So I get P mu over P0 times delta 3 of x minus x of t, and this p square is minus m square in this mostly plus signature. However, if we have a non-relativistic system P0, so let's remember what is P mu. P mu was m times u mu, where u mu was the forward velocity. And forward velocity was, so this whole thing would be m gamma and m gamma v. Now if I go to very low velocities, gamma will be approximately 1, and then this, so in the non-relativistic limit, this goes to m and mv. So in particular, P0 becomes just m, therefore in the non-relativistic limit, this becomes minus m times delta 3 of x minus x of t, which is indeed the mass density of the system. So in the non-relativistic limit, sorry, minus 3. The non-relativistic limit, this minus trace of t mu nu, it reproduces the Newton's equations for at least a single massive particle, and also I can put together a collection of particles, and by the same argument I produce the mass density of the system. Yeah.
Maybe it's a silly question, but if we transform this t mu nu, the trace, it doesn't transform also the P0 component, which is dividing. It will transform, not like a scalar.
No, because
why it doesn't transform? We have
because delta 3 is also not.
Also, it transforms both. Okay. Because we have the x inside. Okay.
Yeah, this combination delta 3 of x, spatial components of x divided by P0 is Lorentz invariant.
It's like 1/2 omega.
Yeah. Thank you.
Okay, so it seems to satisfy at least the criterion for reducing to the equation, to the Newton's gravity or Poisson equation for the gravitational field. Now you can ask, how does it modify the motion of the particles or fields? So we want to couple this field. Of course, we have when I write this equation, I have essentially introduced the coupling between this dilaton, this phi field. Sometimes I call it the dilaton field. I have introduced how this field phi couples to everything else, because in the field theory we say that whenever we write a field theory, we have a T mu nu. Every field contributes to T mu nu. We know how to calculate that. And when I write this equation of motion, I have automatically determined what is the action that leads to this equation of motion. Much to the caveat that I mentioned before, the fact that this statement is kind of circular because you at higher orders you get some correction, but at least at leading order this has completely fixed the interactions of the system. So once I write this equation, then I have already determined that there is an action for this phi, which is what I wrote earlier, is minus, well, I'm going to put some constant here, kappa, that I'll determine it soon. Phi times T mu. So if I vary this action with respect to phi, what I will get is from here I get kappa times box phi, and then from the variation of that term I just get T mu equals 0, and this is minus T squared plus Laplacian of phi equals minus 1 over kappa T mu. So this kappa is just 1 over 4 pi g.
So here we have only phi coupled direction, or what we will have from that action, because the energy momentum tensor will be function of phi only, right?
Oh, so this is when I say S subscript phi, I mean I have only written the part of the action that contains phi. So I imagine that the full action is contains other degrees of freedom and other fields. So the full action is some S of.
So let me within this one. So this equation is only for the field which will be the propagator of our field, or just the exchanging particle. But for the real particles or the source particle, we will have another terms in the action.
Yes, exactly. Yeah, so this trace of the stress energy tensor is really, so let's do the following division. I want to talk about sources, which I call the matter fields, and then I want to talk about the field phi, which I call the gravitational field, or graviton, or dilaton, because I chose it to be a scalar. So I want to separate the action, the full action, into a matter action that does not depend on phi. It only contains other matter fields. Let's just collectively denote them by chi. And then there will be a gravitational action which contains, which vanishes if I set phi to 0. There is a gravitational action that depends on phi and chi. And what I have written here is just the gravitational part. Now this T mu, at this level you can just take as a definition of T mu nu, you can take as a definition of T mu nu to be just the part, the matter T mu nu. So I can put an index m here. So if you take this matter action, you can just follow the Noether procedure to calculate the T mu nu, the stress energy tensor that comes from this part of the action. So that is unambiguously defined. There will be a T mu nu matter. And then I can put an index m here. So then now everything is completely unambiguous. Now if you were to take this T mu nu not to be the matter contribution but the full thing, it would still be almost the same as the matter contribution if you are talking about a non-relativistic system. You can easily verify that this phi field and the contribution that comes from this gravitational part to the full T mu nu is small if you go to the non-relativistic limit. If we go beyond that, then the contribution from this part can be important.
And it includes a self-interaction for the field phi.
Well, at this, if I don't write the matter here, if I put the full T mu nu, yes, it will contain a self-interaction. Yeah. But for the moment, let's stick to this version of the theory. This is essentially a question about how to generalize this model to nonlinear level. As you said, there will be an interaction term for phi. So in general, you can ask what are the higher order terms in phi that one can add to this equation. And at the moment, I'm not fixing that. I'm just trying to fix the leading order contribution at weak gravitational field, at the small values of phi. Yes?
When we were checking if this T mu trace of T corresponds to the Newtonian theory, we used that definition of T mu nu, which we derived from another action we have already.
We derived from what?
How did we derive the T mu nu expression?
I didn't derive it, I just wrote it.
Why not? We tried. We tried like why not this one, right?
Yeah. There can be a derivation of this. I just wrote this because this is and checked it here that it reproduces the correct answer.
So can we check from this action that if it reproduces this T mu nu as the...
Yes, what we can do is that, for instance, now to consider a field theory, point particles are not described by a field, but if you have a field theory, they can describe propagation of particles. You can localize, for instance, some energy momentum in some region and then check that. For instance, the easiest check that you can do is that you have already seen the, or no, this is in these problems, but maybe you have already seen it. You have seen the stress energy tensor for a fluid system, for which if you have a perfect fluid, you can write an action description. If there is no dissipation in the fluid, you can write an action and derive the perfect fluid energy momentum tensor by using Noether theory. So for instance, there you can, what you can do is to verify that this trace of T mu nu for a fluid is, for a non-relativistic fluid, is indeed to a good approximation, reduces to the mass density. And then yes, in general, you can do any field theory that you have. You can consider states in the field theory that describe propagation of particles. Then T mu nu will be an operator. You calculate this expectation value of that T mu nu operator in the state that corresponds to the propagation of a particle, and see that that expectation value reduces to this expression.
But I was going to ask that this T mu nu we also derived, I guess, from the point particle action that we broke down.
Did we? I don't remember.
Something similar to this, because we have a current for that point particle, charge times u times direct delta.
Well, you know, so this point particle action, so let's remember the Noether theorem. The Noether theorem, if you have an action, the Noether theorem gives you, and you have with the symmetry, you have an action and you have symmetry, then the Noether theorem gives you some conservation law. Now, if your action is defined in d plus one dimension, then you get, in general, you will get a conservation law like this from Noether theorem. And then there will be a density, so then there will be a J0, a density that you will calculate, you will integrate. It's a density in a d-dimensional space, right? So here is d plus one dimensional space-time, and the density lives in d-dimensional space. In the case of the point particle action, you have a one-dimensional action. So the charges that you derive there, or the current that you derive there, is just the charge. It's just the absolute value of momentum or energy. It won't be the density. So yes, I'm not sure if you can derive this by applying Noether theorem to the point particle action.
But if we have like 4 directions for the point particle to go and put that extra index nu for the J nu, then we somehow find some T mu nu from that point particle action.
Well, you will have 4 directions. So yes, here you will have these indices, but the upper index that is the one that tells you what is the dimensionality that the action is defined to. Essentially, this is the index that determines what is the dimensionality of your world sheet or world line. And the case of point particle is 1. So it won't be a stress energy tensor.
But what I had intended to ask was connected to this. Maybe that point particle action somehow the non-relativistic limit of this action that we write here, or some connection between them existing. Maybe I try to relate to very different things, but since like the forms of the expression were similar, maybe that one was for the non-relativistic case where we just minimize the proper time intervals of the point particle. But in this case we have the field theory and it's completely different, but maybe they match.
I guess if you have the same configuration, they will match. They have to match. But at the moment, I don't see what are the 2 things that are supposed to match. So what I guess, let me just say this. If you have a field theory, that field theory, you can imagine having a state which describes the propagation of a particle. And then on that state you can you can consider this point particle to act as a source for instance, the gravitational field. So on that particular state, you can write the theory as the gravitational action plus the point particle action. And in fact, that's what we are going to do now. So just to do some to understand how this far field affects the motion of particles. So as I said here, the theory, when I write that equation of motion, the complete gravitational interaction is completely fixed at leading order. So for instance, one can go and ask what is the scattering of two different particles through this gravitational interaction, and therefore once we understand that, we can also answer the question of if, for instance, I have Earth here and something is propagating in the gravitational field, how its trajectory is going to be modified. So these questions can be asked once we have written this theory. The answer to these questions is unambiguously fixed. However, it might be nice to consider a slightly different path, which is to try to couple this phi field to the point particle action. So again, that point particle, we can imagine it that is arising from having some underlying field theory, some massive scalar field. In that theory, there are states which describe massive particles. So on that state, we can consider this point particle action, or we can have macroscopic objects which might have a very complicated description in terms of fundamental fields, but at the end we want some effective description for that macroscopic object, like this chart. So I don't need to describe it by fundamental fields if I just care about how it moves in the gravitational field of the Earth or the Sun. So we go back to the point particle action and ask how would we couple it? How would we couple it to this dilaton field? So let's remember how it looks like before. We had this eta mu nu times dx mu d sigma dx mu d sigma. And now we want to couple it to phi. We want to introduce this phi field here in some way. And the rules of the game were to write something that respects the symmetries of this, respect the Poincare symmetries, and then we also have this reparametrization symmetry of this action. The fact that we can choose any variable to parameterize this word line. And then the easiest thing, and then there were other rules which were asking about the number of derivatives and the number of fields. So if we are imagining some field that doesn't vary much, is relatively is slowly varying in a space, and we want to have the lowest possible number of derivatives acting on it. And then if the field is weak, we want to have the lowest power of the field itself. So the easiest thing to add to this action is to add some lambda phi. So one would be just the original action. I can add this lambda phi as a small correction to the action. And this satisfies all of the requirements that they have. Now we can ask, and of course this phi is a function of x, right? You should imagine that this is the space-time, and then I have this trajectory, and then there is a phi field. some phi of x, phi of t and x. And now I'm evaluating it on the word line, right? So now we can ask again what to do the equation of motion for this point particle. Of course, what we expect is that if we have gravitational interaction and there is a particle moving this, a massive particle moving in this gravitational in this gravitational field, then it should feel the, if it's a non-relativistic system, we should see the usual Newton's second law, F equals ma, with the acceleration a given by minus grad phi. So that's what Newton will tell us. And so what we want to do is to recover that equation in the non-relativistic limit by the good choice of lambda here. Or we want to ask if there is a choice of lambda for which we can recover that. And the answer is yes. So I should just derive the equations of motion for this action, which is, I'll just write the answer. So this, the derivation of this is very similar to what we have done before. Note that this phi depends on x. We are varying this action. This action is, the variables in these actions are the 4 x's. So we are doing a variation of the trajectory of the particle, requiring that it is extremized. So this phi depends on x, therefore we get this d mu of phi. Yes.
This lambda in front of the field will be something like the ratio between the gravitational and inertial mass of the particle. Like, we cannot say that they are the same a priori.
Yeah, something like that.
Like something fundamental.
Yeah. It's related to that. In fact, it's gonna be 1.
Yeah.
So.
Should be one, like, observationally. We put it because we don't know.
Yes. Yeah. In principle, I mean, we know it here, right? From observations, I think, but from the observational equivalence principle. Yeah. In principle, it would depend on the species and stuff, but in reality, it does. Yeah, so we are going to use that. That information is encoded in that equation in the non-relativistic limit, and that is enough to fix it to 1. So what we do is that we take the non-relativistic limit of this equation, and how do we take the non-relativistic limit? Remember that the time derivatives are much smaller than the spatial derivatives. So we consider, so now you can imagine a situation in which this phi is exactly static, or even if it is not static, the system is non-relativistic, therefore we can ignore time derivatives. So if I look at the zeroth component of this equation, it tells me that d by d tau of this expression is 0, which means that 1 plus lambda phi times dx0 d tau is equal to a constant. That constant has a name, is E over m. For instance, if we imagine that we had this gravitational potential and we had something that is coming here from from infinity, from a region where the potential phi was 0. So imagine phi at infinity is 0. And then we have a constant of motion which we can fix at infinity. So at infinity this phi is 0 and we have dx0 d tau. So this E will be the energy of this particle at infinity. So okay, so we have this dx0 d tau which is E over m. Now let me just call it t instead of x here. So what do we learn? dt. So x0 I just call it t. What we learn is that dt by d tau is equal to E over m 1 plus lambda phi. And then we can look at the spatial component of this equation. This was the zeroth component. Then now if I look at the mu equals I component of the equation, this equation, I have d by d tau. I can use this relation to rewrite it as d by dt. So there will be E squared over m squared d squared xi dt squared equals minus 1 plus lambda phi times lambda di phi. Now we are also going to assume that we are in weak field. So this phi is much smaller than 1. So therefore when I have when I have a term which is quadratic in phi, I can ignore it. So phi is much less than 1. The first assumption. The second assumption is that we want to take the non-relativistic limit at which this energy will be of order of the mass of the, sorry, not of order, wrong. E will be, E over m will be approximately 1 up to a small corrections. So now when I take these two limits, this equation becomes d2xi dt squared equals minus lambda di phi, which is the correct equation we were looking for if we set lambda equal to 1. So if I require that I reproduce the correct acceleration for a particle in this gravitational field, I will fix this lambda to be 1. Now we can do a cross check of this formula, which is the following. We can
that formula, is it tau or t? The dxi.
Here,
Yes.
this is t. So I use this relation to express d by d tau in terms of d by dt.
And then you substitute for the spatial part x.
Yes. So I look at the I component of this equation. For the I component, I can raise and lower indices freely because I'm working with mostly plus signatures. So upper and lower I is the same. So I look at the I component, and then there is d by d tau that I use this relation chain rule to relate it to d by dt. Now we can perform a cross check. Once I fix lambda, we can perform a cross check to see. So this point, what have we seen? What we saw is that this point in a background gravitational field, this point particle will have an equation of motion, a trajectory which is which in the non-relativistic limit is correctly described by correctly reduces to the Newtonian result. Another thing that we can check is that now given this coupling between the point particle action and the dilaton, whether we reproduce this source term for the gravity, because now that we have a massive point particle, that will also be a source of gravity. So it both will be affected and will produce the gravitational field. So how do we do that? We can just take this this word line and write it in a four-dimensional fashion. And I only care about the coupling to the phi, so I only care about this term. So if I take that term and write it as a four-dimensional integral by introducing a Dirac delta function, the way it looks is there will be S phi point particle, which is d4x phi lambda is set to 1, and then there is minus m integral d tau times delta 4 of x minus x mu times x mu of tau. Okay, now we can use one of these delta functions, the zeroth, the component along the zeroth direction, to do this tau integral. So that gives us d4x phi times minus m divided by dt d tau times delta 3 of xi minus xi of t. So this is just the usual. Just use the one of the delta functions to do the tau integral, and this will be the result. But dt by d tau is, we know what it is. If I multiply denominator and the numerator by m, it becomes minus m squared over m dt by d tau. And this is nothing but what we call P0. So we get minus m squared over P0, which is indeed what we found as the trace of the point particle action. Sorry, the trace of the point particle stress energy tensor. So this is just a consistency check that we indeed get the correct source for the dilaton. Once we choose lambda so that we have the right non-relativistic equation of motion. Okay, I think I should stop here.
point particle action is for any kind of particle that lives in the matter part of the action. Any kind of field will have its own kind of particle, and this coupling will affect all of them.
Yes. That's why it's called a universal coupling. This kind of coupling, when I couple some field phi to the stress energy tensor of everything, that is usually called a universal coupling. And of course the reason why we write it is because we know that gravity is universal. Other questions?